I'm trying to be not too long and want just to present some results of the work I've been doing recently with some colleagues, and these are related to stellar magnetic fields. Basically, how the questions we want to answer is how do they evolve, and on which timescales they can be stable. Of course, it's a quite complicated and complex problem, I would say. So we will focus only on some aspects and on some peculiar stars. And this work, basically been done with some colleagues. Gustavo Guerrero from University of Minas Gerais in Brazil, and a student working with him, Guilherme Monteiro, Darcio Bonanno in Catania, and Piotr Smolarkiewicz, who is actually the guy who wrote the code we used in Poland. And yeah, some work has been already published, some work is work in progress. The second paper we are about to finish, the third one will take a bit longer. So there are several motivations for studying, for trying to answer these questions I presented, but we are focusing on some peculiar stars, and these are the EPI-BP stars. These are stars with masses between 1.6 and 6 solar masses, show some peculiarity in chemical composition, and they are in general slow rotators because they should be quite old, but they show quite strong magnetic fields and very well ordered magnetic field, very well structured. So from this observational results, one could ask what's the origin of these magnetic fields and on which timescales they are stable. Of course, this kind of question can also be related to other kind of phenomena. For instance, on red giants, there are some recent results in the last years, and they show that there are some magnetic fields stored in their cores, and these are up to 1000 Tesla, so they're really super strong. So this paper by Jim Fuller and collaborators illustrated that there are some observational evidences for that, but we don't know again on which timescales these fields can be stable, because if we can observe them, then it means that they can be stored in the cores of red giants for quite a long time. Of course, this problem is important for many other aspects. Here I mentioned the transport of angular momentum, but as I will illustrate at the end of the talk, of course, one other important point is the connection between the environment in which the exoplanets, especially the close-in exoplanets, evolve and orbit around stars. So there are some stabilizing or many stabilizing or unstabilizing factors for magnetic fields in stars. Here I mentioned some of them: gravity, the intensity of magnetic fields, the initial conditions of the topology of the field, rotation of the star, equation of state, and also differential rotation and thermal diffusivity, which influence the decay of the field. And in this study, I will just avoid to deal with the last three, and will concentrate on the first four aspects. And actually, we will include rotation only in second part of the talk. I'm also, I didn't say that I also want to show some results about dynamos, not only about stability. Let's see how long it takes to present the first part of the talk, and then we will see. So for studying the stability, we start from, we have a numerical setup that basically consists in a toroidal field, pure toroidal field in a stably stratified atmosphere or star. Let's say that we call it star, but basically it's a stably stratified sphere. And And this magnetic field has a radial profile, which we choose in order to confine the field in the middle of to minimize, let's say, boundary effects. And we choose an isothermal equation of states in this stably stratified atmosphere. And the field is unstable, and this is called the stability of purely toroidal fields is called Taylor instability. So basically, a toroidal field in a stably stratified medium at some point, if perturbed, will disrupt, because it's could be in a stationary but unstable configuration. And here then we are dealing with our model wants to address the problem in purely radiative stars, which is of course only one of the possible stars we can observe, but this makes the problem more accessible, because we minimize some way the number of factors that play a role in stabilizing or unstabilizing the field. And all this work is done using the so-called EOLAG MHD code, which is a code working in an elastic approximation, and uses a scheme that resembles the large eddy simulations. So basically, it models turbulence on small scales, and we do so in order to maximize the Reynolds number and the magnetic Reynolds number. So we get to high values of these parameters, as close as possible to real values of real stars. Of course, there are several orders of magnitudes of difference. And we write an energy equation in terms of fluctuations of this potential temperature, theta, using also a cooling on a time scale that we call here, indicate with tau. And we see that in the second equation, that is the momentum equation, we have the effects of gravity, we have the effects of back reaction of magnetic fields on the velocity field, and we can also include rotation when we want. All our studies will be done measuring and in terms of these two frequencies, the Brun-Vasala and the Alfvén frequencies. So one characterizes the gravity of the gravity field that is present in this stably stratified medium, and the Alfvén frequencies instead is related to the magnetic fields. And these simulations that I'm presenting are global simulations of spherical and global simulation of a star. So case one is non-rotating system, and here I show that time evolution of some quantities. These are the basically we take the magnetic fields and we decompose it in Fourier modes and study the different modes that we indicate with m=1, m=2, and so on. And the symmetric one is m=0, and is where the most of the energy is stored, especially at the beginning. Then this starts to decay at some point because other modes start growing. When other modes start growing, it means that basically the field starts step by step being mutating from toroidal to a mixed configuration, toroidal poloidal. Well, I didn't explain it, but toroidal basically means along the equator, and poloidal is all the rest. And here we can see the time evolution of the azimuthal field, so the toroidal field. At the beginning is very well ordered with different polarities, and then this time here is expressed in terms of Alfvén travel times. then it starts to disrupt, and configuration at some point, initial configuration disappears completely. This after 20 FN travel times in these simulations, and this is actually the effect of the instability, of the Taylor instability. So we ran, to do this study, we ran huge number of simulations. They are also rather expensive computationally, with different resolutions. Here, of course, this is just to show the number of simulations, some of the simulations we had, and the number of parameters we studied: gravity, magnetic fields, Bruin-Väisälä frequency, alpha n frequency, and then the density contrast. This parameter delta, that is the ratio between Bruin-Väisälä and alpha n frequency, and then the ratio between the toroidal and toroidal fields when the instability has already surpassed the linear phase. Go back one slide, where the linear phase is basically a phase where all the quantities grow more or less linearly. Here, important quantity here is the growth rate of the instability, gamma, in the linear phase. And then we also quantify the radial number of some modes that we will see that they develop at some point. Here, this is the parameter delta that we will see. It's very important to quantify the effect of gravity of the system, because here we want to, or the main goal of this first part of the study is to see whether gravity can stabilize, can act against this instability. And so depending on the value of gravity, this delta changes, and there's a profile from between 0.4 and 1, that these are the radius that we simulate. So we avoid to, when I said global model, I forgot to say that actually we are just simulating radius between 0.4 and 1. So we avoid to simulate the core of the star, to avoid problems with singularities at the center. And these are first results. So on the left, so these are the growth rates. So this parameter gamma of the growth rate of the stability. On the left, this is plot for different simulations as function of the radius. So we see that with this initial profile, the field does not grow the same way in the whole domain, and this is exactly because of the profile, because the profile is basically Gaussian, and depending on the slope, the field is more or less unstable. And yes, here the difference between these simulations is gravity. So this at 0,1 simulation has the lowest value of gravity, and then this at 0,9 has the highest value of gravity among these plotted simulations. So we already can see from here that the growth rate decreases with gravity. But then here, when we plot the growth rate, the global growth rate, so the average field, as function of this parameter delta, we see that there are different regimes, and then when delta becomes very large, it means that the gravity is very large, because we are keeping constant the magnetic fields in this set of simulations. Then there is a steep decrease of the growth rate. And we get some point in where the growth rate is not 0, but anyway, it goes to very small values here. So we cannot claim that at some point we found the value of gravity that completely stabilizes the field, but the trend seems to indicate that that's the case. But numerically, this with with our tools, this is not possible. This was not possible to be demonstrated. And this is just an example of what happens when we have a strong value of gravity, so 500 meters per second squared, and quite strong magnetic fields. After more than 100 fan travel times, the field is still more or less in its initial configuration. This means that gravity is actually working quite well for stabilizing the field. Then we run other sets of simulations to study the dependence on the initial magnetic fields, on its intensity. So here we can see that we have 3 sets of simulations with 3 different values of gravity, and then the B0 changes. I just realized that I can go this way. Sorry. And yes, here we plot exactly what happens to the m equal 0 and m equal 1 modes, also m equal 2 modes, with different values of magnetic fields and also changing the gravity. So we can see that when we keep constant magnetic fields, changing the gravity, yeah, the growth is less steep. But also when we keep the gravity fixed and we change the magnetic field, for instance, these blue lines, you can see that at some point the instability is suppressed quite a lot. This when the magnetic field is 100 times weaker, it's difficult to see the development of the instability. But I have to say, then we have to stop here the simulation because this really takes forever, because with basically 1 fan travel time here, it's much longer than 1 fan travel time here, exactly because that depends on the intensity of the field. And these are also 2 cases, 2 different simulations with same gravity but different magnetic fields. And we can see that, for instance, at the same time step, same time, fan travel times, in one case, the magnetic field is more, this initial configuration is kept much well here, with weaker fields, while here some mode starts disrupting the initial configuration, and then the instability occurs on a shorter time scale. So here it's after more or less 60 fan travel times, and in this case instead after 80. Then the final configuration is pretty much the same. Well, in this plot, we just quantify what happens to the toroidal and poloidal components, and we see that the magnetic fields, the magnetic energy, actually, there should be something, well, maybe I should have plotted in logarithmic here, because the magnetic energy does not go to 0, or it seems here. But however, what matters here is that the ratio of poloidal and toroidal grows a lot after many fan travel times, and then reaches more or less, oscillates around 1. So the poloidal field becomes as strong as the toroidal field. And here we try to explain why this happens on the right part of so on the right plot. These are power spectra of the kinetic and magnetic energy, and we see that for these simulations at the beginning, especially here in the kinetic energy, we see that the intensity of the spectra is quite low, but then it grows a lot and then reaches the value of basically fully developed 3D turbulence. And so this might be basically the demonstration that the instability makes the field, makes the velocity field, which at the beginning was basically no velocity field, everything was at rest, then makes it completely turbulent, and then this leads to the development of poloidal components. While on the plot on the left, I just show the growth rates for all sets of simulations, with also by changing magnetic fields. These blue, yellow, and black dots. While the stars show some simulations with higher resolutions that actually behave quite well, and in some cases we even get the same growth rate, so indicating that there is some numerical convergence, but not in all cases. In some cases there is some disagreement with values that obtained at lower resolutions. So the physics is the same when we change resolution, but we cannot claim that the value that we get are convergent in time. That's why it's difficult to extrapolate this hypothetical threshold for the stability of the field. So to extrapolate which gravity can stabilize some magnetic field. And this is just to show that actually this is an open debate. Did other people, for instance, this is work by Rennerart, his collaborator. They got a bit different results previously. For instance, in this simulation, they show that by changing the radial gravity, the growth rates of the m=1 mode remains the same, in very similar setup. But so we are still trying to understand what is the difference with these simulations they run. They actually start with a bit different initial conditions, but it's mainly possible that they're investigating a smaller parameter space in terms of gravity, and so they get this effect. But still, this is not obvious. And matter of fact, our simulations, to my knowledge, are the first that show that this Taylor stability can be obtained also with anelastic simulations. So simulations that a numerical scheme that filters out the sound waves, basically. Then we can add rotation, and this is work in progress that we are writing these days, hopefully soon to be submitted. And the effect of rotation in linear theory is predicted to stabilize the field, but then what happens in numerical simulations is not so trivial. So for instance, here we have three different sets of simulations, well, three different simulations, the same initial configuration of the field, the same initial intensity of the field, and value of gravity, but different rotations. And plotted are the normalized energy in terms of modes, so the m=0 mode, and then all the other modes. So for when the rotation is 300 days, it seems that, well, first of all, we see that not all the quantities grow linearly. It's more complicated to find a linear phase of the instability in these three cases. For the 300 days rotation, we would expect the stability develops faster, but looking at this plot, it seems that actually it takes longer. Remember, here we are plotting quite huge values of Alphen travel times. These stabilities are thought to develop on a few Alphen travel times, but here we are at the order of 10,000. So they are already quite stable, but the results here appear to be a bit counterintuitive. So we tried to understand what was going on, and let me show a couple of videos about this. So this is the case. Can you see this video? I hope so.
Yep.
This is the case, the non-rotating case, and these are the initial magnetic field lines that we plotted more or less like spaghettis, because we want to feed the stereotypes that we Italians like spaghetti. And let's see what happens. Everything is quite stable at the beginning. Then some perturbation, and then everything gets completely mixed up. This video more or less runs on the order of 5,000 Alphen travel times. Then let's see what happens when the rotation is instead 10 days. At the beginning, there is some more trouble, although this is time scale much longer. It's more or less 20,000 Alphen travel times. But then the configuration remains more or less the same. So we don't get that very mixed configuration that we got in the non-rotating case. When the rotation is quite fast, actually the toroidal field, the initial toroidal topology of the field tends to stay conserved. So we try to understand a bit better this, so we plot here the initial the decay, the initial time of decay of the m = 0 mode for all the simulations. So here a simulation with 300 days of rotation, and then lower values of the period of rotation. In terms of, well, we plot here actually the number of rotations that are necessary to get the m = 0 mode to start to decay. And we see that there is some value around 30 days where this number of rotations increases a lot. So we suspect that around here there is a sort of threshold between 20, well, 15, 30 days, where this trend changes, and then the field gets stabilized much more. And then we get the effect that we saw in the video, where basically the toroidal topology is conserved. Another way to see it is to plot the toroidal to toroidal ratio. Here we plot it again in terms for each simulation, and we see that, for instance, on the left here, we have that the ratio grows up around 1. This is the non-rotating case, but then this growth actually takes place always later when we decrease the rotation. And in some cases, like here, for instance, we are 30 days, and this blue line is 10 days, and actually it doesn't grow at all after 20,000 Alphen travel times, which I tell you, it's really a lot. So this means that the toroidal component cannot develop, and the field is some way stabilized. Then we saw that so we suspected also for these values, especially this 30 days rotation, at some point this should grow, and this might be consequence of the development of turbulence due to the instability. But the message is that when we add rotation, really the Taylor instability changes a bit its behavior. So it's not easy to understand what is the linear phase of the stability. So take-home messages from this part is that we managed to do some global simulations, Taylor instability in elastic approximation, and both gravity and rotation can stabilize the field, and initial intensity and initial field configuration have also play a role in this. And they might indicate that for this APBP star, the threshold of 300 Gauss fields observed, so we basically do not observe any star with fields lower than 300 Gauss, might be consequence of this sort of this physics that I indicated here. I want to have hopefully some more minutes to show some results instead of a dynamo simulation. So I will be short, and these are simulations that we performed about a star that is called EKEri, and it's a very slowly rotating evolved P stars. It has the polar field observed around 300, bit less than 300 Gauss. Again, we don't know whether the field is originated by dynamo or has a fossil origin. And the problem is that this star is not only radiative, so we don't know which is its internal differential rotation, and this makes our life quite complicated, because internal differential rotation might play a very important role in amplifying the field. So, but we got the radial setup, so the radial structure from some stellar evolution code, and then we put it in our simulation. So we have a radiative core and then a convective zone. Here we plot the radial velocities of inside the star, and then we also added an external very thin radiative layer in order to again avoid boundary problems, and we put an initial toroidal field to see what happens. So we let the star evolve. We see that convection is still there, and some strong toroidal fields develop, especially at the boundary between convective area and convective zone and radiative zone. What is important is that here we develop some internal differential rotation, and that again we don't know whether this is the real differential rotation of the star, but this is the result that we got from our first set of simulation. And this is the global evolution of the magnetic field. So we see clearly a growth that is a dynamo growth of the total field that we also analyze in terms of mean and turbulent field. So these simulations seem to indicate that the star presents some dynamos, but I was not honest because what we did is that actually when we simulated the star rotating with 309 days, this growth really was not much. So what we did is we increased the rotation, because we know that the star previously was rotating rotating faster. So when the star was rotating, if the star with the same structure was rotating in 154 days, then we can observe this growth of the field. So now what's left to be demonstrated, and the reason why this paper is not finished yet, is that we have to investigate actually what is the structure of the star with this rotation, and then rerun the same simulation and see whether actually the field grows also, so I can present the dynamo growth also with different internal structure. Because in this way, if the field is still there, then we can extrapolate results from previous study saying that the field can be stored on certain time scales, and then the field can be not of fossil origin, but perhaps of dynamo origin, coming from earlier evolutionary time of the star. It's quite complicated thing to be demonstrated in my opinion, but this is what we can do with these tools. Yeah, I want to finish. I talked with Guillaume, and perhaps I can say some words about work I hope I can do in Barcelona starting from next fall. That will make use also of some of the tools that I'm using for these studies that I presented. Topic is similar, but not quite, because here my project will consist in seeing what is the interaction between the some close-in orbit in some exoplanets on close-in orbits, and stellar dynamos and stellar activities. So stellar dynamos, as I said already, they are driven by a high number of factors. For instance, boundary conditions, for instance, very important forcing, rotation, the effect of tachocline, which is the area, for those who don't know, the area, the shear zone between radiative and convective areas in stars in general, especially for this was named tachocline for the sun. Then convection, turbulence, tides, and also, last but not least, we don't know exactly what is the connection between dynamo and stellar activities. We can say that stellar activity is influenced by magnetic fields, and magnetic fields are influenced by stellar dynamos, but this is not really still a field to be explored. My work will concentrate on what happens on boundary conditions, so on especially on stellar coronas, and the role played by currents in the corona and outflows. And then I will try to study what is the effect of planetary induced tides on stars with different values of rotation. So in terms of influence of currents in stellar coronas, my idea that I proposed to be investigated is that actually exoplanets in close-in orbits that are evaporating, they might be inducing some currents in stellar coronas. Actually, currents coming also from their evaporation rates. I know that one assumption that is made usually is that actually in higher atmospheres of exoplanets there is no current, but then if there is evaporation of some ionized gas, then this is by definition some current, I would say. But anyway, this needs to be explored, and the idea is that these currents can actually influence in terms of boundary conditions the dynamo efficiency of stars. This is something that we, together with my colleague Alfio Bonanno, we demonstrated analytically with using a model of so-called alpha square dynamo, and so that depending on the mutual interaction of currents and magnetic fields in the corona, the dynamo can be more easily excited or suppressed. And here I'm just plotting the dynamo number in terms of this beta parameter. This is the force-free, the so-called force-free parameter, because one assumption is that in the coronas all the magnetic fields are in a force-free configuration. And then the other part of the project will consist in performing simulations to see what is the influence of planetary tides on dynamo. So the idea is that the planets orbiting a star, although very tiny, but is constantly forcing the star with some tidal interaction. This was already modeled with some mean field model by Frank Stefani and collaborators. They did it for the sun, for the solar system, because there is always this story that every now and then comes up that Jupiter is orbiting in 11 years, and Sun shows an 11-year cycle, actually 22 years cycle in terms of magnetic activity. And so there are some, I would say the majority of people say that this is a bit esoteric, but then some people started to see whether some, especially tidal alignment of planets can trigger some oscillations in some basic models of stellar dynamo or solar dynamo, and this seems to be the case. Then, so there should be some tiny effect. We don't know the role that it has on actually setting the solar cycle, and we hope we can say something more about this in one sense or the other. And that's all for now.
Okay, thank you, Fabio. Yes, and happy Sant Jordi Day. Today it's the Diada, Catalan National Day, and we usually give a rose and a book to your significant other. You'll get the book.
Happy Sant Jordi. I thought it was a holiday, but it is not, right?
No, it's a very special celebration that you do at work. Well, it's so people don't live and celebrate in the streets, but this year it's a bit strange. Okay, happy Sant Jordi. Somebody, questions, comments you would like to ask Fabio? Turn on your video and just raise your hand or say something in the chat. Let me see.
Yeah, I have a question, William.
Okay. Aldo, go ahead.
Yeah, thank you, Fabio, for the presentation. I have a couple of maybe a bit scattered questions. So, so first, you mentioned in the beginning, mostly in the introduction of your talk, about the giants that have this, let's say, which have these depressed dipole modes, right? Which have been thought to be because of the dissipation of energy in the magnetic core, right? So, is it possible to build simulations with the codes that you have, where you can try to actually model this in the sense that you inject some acoustic energy, and then you see what happens when you have a strong magnetic field in the core, and see if this really removes energy from the acoustic dipole?
So, acoustic, actually, I would say no, because the code is anelastic.
Okay, yeah, sure. Sorry, you mentioned.
But yeah, we could actually. So the idea is that we could find some stable configuration of the field, and then perturb it with, for instance, a Gaussian perturbation of the velocity field.
Mm-hmm.
And yeah, this could be a way to study the stability, for how long fields can be stable. Of course, one should at some point add some more realistic values, especially for the stratification in the core of these red giants.
Mm-hmm.
I mean, that results, I guess, that is both theoretical and yeah, and there is also observational results. I know that been also disputed by some other parts of the community. And yeah, one reason to be disputed is also that we cannot really demonstrate that fields can be stable for this long time scales. So yeah, I would say,
the fields you need are very strong, you said, right? So like something like 10 to the 7 Gauss or something like that.
Yeah, and we saw that actually in our simulations, when the field is stronger, then it gets a bit more unstable. Yeah. So, but the values of gravity at in the cores of the red giant are also much stronger.
But yeah, exactly. So it's just gravity. So the equation of state, given that the generate core, does that play a role in the stability, or that doesn't really matter?
So we didn't investigate that yet. Basically, I say that we used an isothermal equation of state, but basically it's a polytropic equation of states, but with a very high, so the index is very high, so it's basically isothermal. We should investigate also how it changes with equation of state, but especially how it changes with the gravity profile, I would say, and rotation. This should be the most important factors. So if we have, of course, red giants, the core should not be very fast rotating. So rotation should be quite slow, but gravity profile can actually confine the field in some area. This could be the idea, but I don't have an opinion in one sense or the other, because we didn't demonstrate whether or not the fields can be stable or not.
Okay. I have more questions if there are no other. Can I go ahead?
Go ahead.
Go ahead, because probably Daniele wants to make a comment, but he.
Okay. Yeah. Then also there are some results also relatively recent related to magnetic braking, right? Because magnetic braking, well, so rotation is being used usually as to age stars, right, with this gyrochronology. But there have been some results now that show that the braking mechanism seems to change. Maybe this is related to a change in the type of magnetic field. So when stars get a bit older than the sun, the magnetic braking seems to be affected in such a way. Do you have an idea about these things? This work done by group in Hawaii, Jamie Tayar, and these people.
I don't know this work, I must say. So I cannot really express an opinion on that. But I suspect that magnetic braking can change, because if we change the topology of the field, then also the braking mechanism, I will not say change drastically, but change at least a bit. So how the magnetic braking works in transporting angular momentum, I think is still a bit mysterious, at least for me. I don't know, maybe you know more about this. But I suspect that the topology of the field might play a role, yeah, definitely. And so this mixed poloidal and toroidal configuration, yeah, might change the braking and magnetic braking. But it's just speculation, really.
Okay. Thank you.
Okay. Thanks, Aldo and Fabio. Daniele.
Yes. Hi, Fabio. Nice talk. Interesting. I have a couple of questions. One is pretty general, and actually it's maybe to other people, to Aldo or to anybody. When you know that the AP and BP stars, as Fabio mentioned, they have quite large magnetic field, and you have like a threshold, no? So at least 300 goes. No? Now the question is there any bias that favors this? I mean, that maybe there are stars, AP and BP stars with lower magnetic field, but they are much less likely to be detected, or it's a real physical thing? That's the first question. And then the second is just if you can clarify a little bit better when you implement a rotation, what does it mean exactly? You have a rigid rotation or a rotation of the core, or how does it work in the code? Thank you.
So I start from the second question, then we discuss the first. Yeah, in this case is rigid rotation. So the body is rotating without differential rotation. Originally, we wanted to study differential rotation and shear and see if it was a dynamo, but then this suddenly became too complicated, and we went back to study the easier problem, entre comillas. Yeah, because if we didn't study the rigid rotation case, we could not understand. And indeed, when we put the rigid rotation, it's already difficult to understand how the different modes behave, the growth of different modes behave. But with this knowledge, then we can then do another follow-up and then add internal differential rotation And then the idea is that there might be some dynamo effect, even some only magnetic alpha dynamo effect. So without convection, we can have dynamos. But let's see, this has to will come. Then for the first question, so I can tell you that when I read about this problem, the first thing I thought was, okay, maybe there is some observational bias. So we cannot observe fields that are weaker than 300 Gauss. But that does not seem to be the case, because actually there are techniques that allow to observe fields that are, I think, actually down the order of 10 Gauss. But I'm not an observer, so somebody else can comment on this. It's more than welcome. So I'm still wondering if this is physical or not. But I don't have an answer to that.
But the observations are, so these magnetic fields are mostly determined through what, Zeeman or splitting, or through polarization measurements, or what?
Polarization, I would say. Spectropolarimeter.
Just a clarification. Can you tell us very quickly what's an AP star? Why is the A, I guess, is spectral type, but the P comes from peculiar, right?
Yeah, peculiar. Yeah, it's chemical peculiar, because they show some spectral lines that are peculiar, and one would not expect in those kind of stars.
Is it understood the origin of the peculiar lines, if it's connected actually with this? I heard even things about spots having these lines and that they rotate and you see the modulation. And even I read a couple stars showing even trans-Uranian lines from trans-Uranian elements. I'm not sure it's confirmed or not, but there are very, very peculiar objects. I don't know if this is this is the same sign of the stars, but more or less the physics of all this peculiarity is connected to this magnetic field. Is it well understood?
I don't think it's demonstrated that it's connected to the magnetic field. And so that the peculiarity should come from some mixing, but as far as I know, but again, it's not clear how these elements got up to the to stellar atmosphere. I don't know if Aldo can comment more on this. Maybe he knows more.
No, not really. No, but I think there is the fact that there are very large concentrations of some element, which are usually weird in a sense. I'm not sure transuranium element, but for sure there are some which show very large enhancement in S-process elements like neodymium, so rare earths and things like that, right? And so the point is that any macroscopic mixing would keep more or less the relative abundances of these elements fixed to a normal galactic value. And the fact that you see this large enhancement could say that there is some microscopic mechanism transporting preferentially one element with respect to other. And this is why people think this may be related with something related to how do you say, radiative accelerations, interactions with magnetic fields, something like that. But I think that's just a kind of speculative. Yeah.
Okay, thank you.